It arrived from a star we have never identified, in a planetary system that may no longer exist. It carried chemistry that does not match anything in our solar system. It may have been traveling through the galaxy for longer than Earth has existed. And on June 22nd, 2026, James Webb Space Telescope data published in the journal Nature revealed something about it that stopped planetary scientists cold. This object, this visitor from the darkness between the stars, is more than 10 billion years old. It formed when the universe itself was less than 4 billion years old. It has been wandering the galaxy since before our sun was born, and what it is made of tells a story about a place so cold, so ancient, and so fundamentally different from our own corner of the cosmos that the word alien, in its truest scientific meaning, has never been more appropriate. This is the full story of what James Webb has revealed about 3I Atlas, and it is more extraordinary, more unsettling, and more scientifically important than almost any coverage has managed to convey. Start with what 3I Atlas actually is and where it came from. The comet was first detected on July 1st, 2025, by the NASA-funded Atlas Survey Telescope in Rio Hurtado, Chile. From the moment astronomers calculated its trajectory and velocity, they knew they were looking at something that did not belong here. It was moving too fast for anything gravitationally bound to our sun. Its path through the solar system was hyperbolic, meaning it would curve around the sun and continue outward into interstellar space without ever being captured. It came from the direction of the constellation Sagittarius, toward the heart of the Milky Way, and it was moving at more than 130,000 miles per hour, roughly 210,000 kilometers per hour, far faster than any comet that had originated in our own solar system could achieve at the same distance from the sun. It was only the third interstellar object ever confirmed to have passed through our solar system. The first was Oumuamua, discovered in 2017, a mysterious cigar-shaped object that sparked years of controversy because its behavior was unusual and did not neatly fit any known natural explanation. The second was 2I Borisov, discovered in 2019, a more conventional comet that confirmed interstellar visitors were real and not a fluke. But 3I Atlas was in a different league from both of its predecessors. It was brighter, it was faster, it was larger, estimated at roughly 7 miles or 11 kilometers across, making it one of the largest cometary nuclei ever observed at any distance. And it was far more active than Oumuamua or Borisov had been, outgassing dramatically as it was warmed by the sun and generating a coma, the cloud of gas and dust surrounding the nucleus that made it visible to a wide range of telescopes. The James Webb Space Telescope turned its instruments toward 3I Atlas for the first time on August 6, 2025. It used the near-infrared spectrograph, IR spec, to analyze the light coming from the comet's coma, breaking it into its component wavelengths and reading the chemical fingerprints encoded in that spectrum. The result was immediate and unexpected. Webb detected carbon dioxide, water, water ice, carbon monoxide, and carbonyl sulfide in the coma. That list alone confirmed that 3I Atlas was a genuine comet carrying complex chemistry from its home system. But the number that stopped researchers in their tracks was the carbon dioxide to water ratio. It was the highest ever observed in any comet, interstellar or solar system. In comets from our own solar system, carbon dioxide is typically present, but in more modest proportions relative to water. The fact that 3I Atlas had such an extraordinarily high carbon dioxide abundance relative to water was immediately recognized as a signature of its alien origin, a chemical profile that pointed to a formation environment fundamentally different from the conditions that produced our own comets. The abundance of carbon dioxide in the coma of 3I Atlas could indicate that the interstellar comet has a heart that is intrinsically rich in carbon dioxide and could reveal more about the conditions in which 3I Atlas formed. Carbon dioxide freezes and remains solid at temperatures significantly colder than water ice. A comet, rich in carbon dioxide relative to water, formed in a region cold enough to condense and preserve large amounts of frozen CO2, which means it formed further from its parent star in a colder, more distant region of whatever planetary system gave birth to it. The chemistry of a comet is, in effect, a geological record of the temperature and composition of the nebula in which it formed. 3I Atlas was carrying a record from a place far colder and far more carbon-rich than the outer regions of our own solar system. Then came December 2025 and the second round of James Webb observations that produced the results published in Nature on June 22, 2026. As 3I Atlas began moving away from the sun after its closest approach in late October, astronomers seized the opportunity. The comet had been freshly warmed by perihelion, its ices had been converted to gas and were actively escaping into the coma, and the chemistry of the comet's interior was being exposed and vaporized in a way that made it ideal for spectroscopic analysis. Webb turned its MIRI instrument, the mid-infrared instrument, toward 3I Atlas on 2 separate dates in December 2025 as the comet retreated outward through the solar system. What MIRI detected was methane. NASA's James Webb Space Telescope collected its first mid-infrared chemical fingerprint of an interstellar object during a recent revisit to Comet 3I Atlas, detecting methane as the comet traveled back out of our solar system after whipping around the sun. The methane detection is one of the most scientifically striking findings of the entire 3I Atlas observing campaign, and understanding why requires a brief explanation of what methane means in a cometary context. Methane is an extremely volatile molecule. It freezes at temperatures approaching minus 182 degrees Celsius. For methane ice to be preserved inside a comet for billions of years, the comet must have spent essentially all of that time in a thermal environment cold enough to keep the methane frozen. Once a comet is exposed to any significant source of heat, the methane boils off rapidly. The fact that 3I Atlas still had methane to release when it was warmed by our sun means that its interior had been kept at extraordinarily cold temperatures for its entire history, temperatures achievable only in the deep outer regions of a planetary system or in the interstellar medium itself, far from any star. The December 2025 MIRI observations also detected carbonyl sulfide, a molecule containing carbon, oxygen, and sulfur that is found in some solar system comets, but is particularly associated with regions of interstellar space where complex sulfur-bearing chemistry occurs. The combination of methane, carbon dioxide, carbonyl sulfide, and the earlier detections of carbon monoxide and water ice built a chemical portrait of 3I Atlas that was unlike any comet previously studied. NASA has confirmed that the data proves Comet 3I Atlas is like nothing we see in our own solar system, and that the interstellar visitor formed in a distant corner of the galaxy markedly different from the conditions found within our solar system. The age determination published in the June 22nd Nature paper is perhaps the single most staggering finding of the entire campaign. Analysis of data from James Webb Space Telescope observations revealed clues to the comet's origin, including the fact that it appears to be over 10 billion years old, making it the oldest comet ever studied. The age estimate comes from a combination of the comet's chemical composition, its trajectory, its velocity, and modeling of stellar populations in the region of the galaxy from which it appears to have come. The Milky Way is approximately 13.6 billion years old. A comet that formed 10 to 12 billion years ago came into existence when the universe was less than 4 billion years old. Our own sun formed approximately 4.6 billion years ago. Earth formed roughly 4.5 billion years ago. 3I Atlas was already more than 5 billion years old before the disk of gas and dust that eventually became our solar system had even begun to collapse under its own gravity. Whatever planetary system gave birth to this object had already lived and possibly died before the sun ignited for the first time. The planetary system of origin is almost certainly gone. A star old enough to have produced this comet 10 billion years ago would be a star that formed in the early universe, when stellar populations were very different from today. Massive, hot, short-lived stars dominated the early galaxy. Many of those stars have long since exploded as supernovae, leaving behind neutron stars or black holes. A star massive enough to host the planetary system that created 3I Atlas has almost certainly already ended its life in a spectacular stellar death. What 3I Atlas carries, the carbon dioxide, the methane, the carbonyl sulfide, the water ice, is the only surviving remnant of a planetary system that has not existed for billions of years. The comet is a fossil. It is the most ancient artifact humanity has ever had the opportunity to study directly. The full observing campaign that produced the June 22nd findings was a testament to the speed and coordination with which the astronomical community mobilized around 3I Atlas after its discovery. NASA's SPHEREx mission, the spectrophotometer for the history of the universe, Epoch of Ionization, and ICES Explorer, observed the comet from August 7th through 15th, 2025, capturing infrared light from the dust, water, organic molecules, and carbon dioxide in its coma. In December 2025, SPHEREx reobserved 3I Atlas and detected a sharp increase in brightness, along with a richer inventory of organic molecules than had been seen in the August observations. The organic molecules detected by SPHEREx were not identified at the level of individual compounds, but their presence added to the growing picture of 3I Atlas as a carbon-rich, organically complex visitor from the early galaxy. The European Space Agency's JWST spacecraft, the Jupiter Icy Moons Explorer currently en route to the Jovian system, briefly turned its Janus navigation camera toward 3I Atlas on November 6, 2025, capturing one of the most visually striking images of the campaign. The image, processed to reveal the structure of the comet's coma, showed the comet glowing against a background of stars. its coma extending asymmetrically in the direction of the sun's light pressure. Data from that brief encounter was downlinked to Earth over 2 marathon 11-hour sessions in February 2026, a laborious process that nonetheless yielded science that no Earth-based telescope could replicate, given JUIC's unique position in the solar system at the time of the observation. NASA's Hubble Space Telescope reobserved the comet on November 30th, 2025, with its Wide Field Camera 3 instrument, adding high-resolution visible light imaging to the multi-wavelength portrait that the campaign was assembling. In January 2026, TESS, the Transiting Exoplanet Survey Satellite, conducted a special observation run on 3I Atlas on January 15th, 18th, and 19th, gathering data specifically designed to study the comet's activity level and rotation rate. The rotation data from TESS will help scientists understand the comet's physical structure and how its nucleus is shedding material as it is heated by the sun, which in turn constrains models of how old and how thermally processed its outer layers have been. The Breakthrough Listen program, the most well-funded search for extraterrestrial intelligence in history, also turned its Green Bank telescope toward 3I Atlas during its December 2025 closest approach to Earth. The search was explicit and honest. Scientists analyzed more than 471,000 candidate signals from the comet's direction across multiple radio frequency bands. Every single candidate turned out to be consistent with human-generated radio frequency interference from Earth. No narrowband signal, no repeating pattern, no anomaly that could not be explained by known abiotic processes or terrestrial contamination. 3I Atlas is definitively and conclusively a natural object. It is not a probe. It is not a signal. The chemistry is consistent with chemistry. The trajectory is consistent with the gravitational dynamics of interstellar space. What it is remarkable enough. To understand why the combination of age and chemistry is so scientifically significant, you need to understand what the early universe was actually like when 3I Atlas formed. When the universe was less than 4 billion years old, it was a very different place from the one we inhabit today. The first generation of stars, astronomers call them population 3 stars, had formed from almost pure hydrogen and helium, the only elements produced in significant quantities by the Big Bang itself. Those first stars were enormous, many times more massive than our sun, and they burned fast and died young in catastrophic supernova explosions that forged the first heavy elements, carbon, oxygen, nitrogen, silicon, iron, and scattered them through space. The second and third generations of stars that followed were able to incorporate those heavy elements, building the richer chemical environment that made planets, comets, and eventually life possible. A comet that formed 10 to 12 billion years ago formed in a stellar system assembled from this early generation heavy element material, in a universe still learning how to make complex chemistry. The carbon to oxygen ratios, the sulfur abundances, the proportions of different volatiles in that ancient planetary system were set by nucleosynthesis processes in the stellar generations that preceded its formation. Processes that operated under conditions very different from those that produced our own solar system's chemistry 4.6 billion years ago. The high carbon dioxide to water ratio in 3I Atlas, the methane abundance, the carbonyl sulfide, are all consistent with a chemistry set in a different era of the galaxy's chemical evolution. Reading that chemistry through JWST's instruments is, in a very real sense, reading a record of what the Milky Way was like 10 billion years ago, before our own solar system existed. The story of how this single object connects to the deepest questions in astronomy is difficult to overstate. Dark matter and dark energy govern the large-scale structure and evolution of the universe. Nucleosynthesis in stellar cores creates the elements. Planetary system formation distributes those elements into comets, asteroids, and worlds. Those comets get ejected into interstellar space by gravitational interactions. They drift for billions of years, and occasionally one of them drifts through our solar system while we happen to have the instruments to read what it carries. The entire chain of cosmic processes, from the Big Bang to stellar evolution to planetary dynamics to interstellar drift to a single detection event on July 1st, 2025 in a telescope in Chile, is written in the chemistry of 3I Atlas. Every molecule Webb detected is a data point in that story. What makes the 3I Atlas story specifically terrifying in the scientific sense? The word terrifying meaning something that confronts us with the full scale and strangeness of the universe in a way that makes us feel the smallness of our own existence and knowledge, is the age combined with the chemistry. A comet born 10 to 12 billion years ago in a stellar system that no longer exists, carrying methane ice preserved at temperatures near absolute zero for billions of years, arriving in our solar system for the first and only time in its entire existence, and passing through within a few years of us having instruments sensitive enough to actually read its composition in detail. The timing is either an extraordinary cosmic coincidence or a hint that interstellar visitors like 3I Atlas are more common than we previously believed. and that we were simply not watching carefully enough to see them before. The Vera Rubin Observatory, which began its full legacy survey of space and time on June 30th, 2026, is the instrument most likely to resolve that question. Its sky survey cadence, scanning the entire southern sky every few nights with a 3.2 gigapixel camera, means that any new interstellar object crossing into the inner solar system has an unprecedented probability of being detected early, while it is still distant enough for follow-up observations to capture the full arc of its journey. If Oumuamua was detected too late for meaningful physical or chemical characterization, and if 3I Atlas was discovered early enough for an extraordinary scientific campaign, then the next interstellar visitor, designated 4I when discovered, may be caught earlier still, possibly while it is still beyond Jupiter's orbit, giving telescopes more time to study it at a wider range of distances and thermal conditions. The Roman Space Telescope, launching August 30th, 2026, adds infrared sensitivity to faint, cold, distant objects that ground-based surveys might miss. The combination of Rubin's wide-field sky cadence and Roman's deep infrared sensitivity creates a two-instrument early warning system for interstellar visitors that did not exist before July 1st, 2025. The solar system has been receiving interstellar guests for its entire 4.6 billion year history. We have only detected 3. The real number is almost certainly vastly larger. What changed is not the number of visitors. What changed is our ability to see them. What James Webb revealed about 3I Atlas is a portrait of the ancient galaxy in a comet-sized container that traveled billions of years to reach us. A chemistry born in conditions colder than anything in our solar system. A nucleus preserved in interstellar cold since before our sun lit up for the first time. An age that puts it in the early universe, when the stars burning in the Milky Way were a different population, when the heavy elements that make up planets and people and telescopes were still being forged in stellar cores that have long since exploded and dispersed. In a set of JWST images and spectra, published in Nature on June 22nd, 2026, that represent humanity's most detailed chemical portrait of another planetary system's ancient chemistry ever assembled. This object, this wanderer, this 10 billion-year-old fossil of a dead star's dead planetary system, spent most of the age of the universe traveling through the dark between the stars. It had no idea we were here. It still does not know we exist. It carried no message intended for us. It launched no signal. It bore no intention. It simply passed through, following the gravitational path that a long-dead planetary system had set it on billions of years before our species had evolved the ability to ask questions about the universe. But we watched it pass. We scrambled every major space telescope in our fleet toward it within days of its discovery. We used Webb's infrared eyes to read the chemistry of its coma across multiple wavelengths and multiple observation dates. We used Spherex to map its dust and organics. We used JWST to photograph it from an unusual angle in the outer solar system. We used Hubble, TESS, the Green Bank Telescope, Gemini, the Las Cumbres Observatory Network, and Meerkat to study it from every angle and in every wavelength accessible to us. And from all of that data, assembled by hundreds of scientists across dozens of institutions on multiple continents and published in peer-reviewed journals, we built the most complete portrait of any interstellar visitor ever assembled by human science. What we found was not comforting in the way that simple answers are comforting. What we found was true, and the truth, as 3I Atlas has just made extraordinarily clear, is that the universe is far older, far larger, far stranger, and far more full of chemistry we have never encountered than anything we imagined before it arrived. The interstellar medium is not empty. It is full of ancient travelers carrying the chemical records of stellar systems that have lived and died while our own planet was still being assembled from dust. Some of those travelers will pass through our solar system in the decades ahead. Most of them will pass unseen. But with the Vera Rubin Observatory now scanning the sky every night and the Roman Space Telescope about to join it from orbit, the odds are shifting. The universe has been sending us messages, written in chemistry for billions of years. We are only now building the instruments to read them.